what I'm going to do right now for the rest of the meeting is that I'm going to go over some high-level information about integral calculus, try to give you some idea of how integral calculus is going to work. All right. Calculus 1, you see this very clearly that they break it in two different branches in calculus. The first part, or 3/4 of calculus 1, we focus on differential calculus. And in the second part of the course, we focus on integral calculus. So technically in calculus, you break it down into two parts, differential calculus and integral calculus. So for differential calculus, again, you take derivative of the function using differentiation rules, all the derivative techniques in all the application, most of the applications that you would like to see in actions using derivatives. Now, at this point, we're going to move on to integral calculus. So integral calculus focus on finding the distance given velocity. Right. Here for integral calculus, you have something called distance and area problems. If differential calculus tell you about rate of change about finding the slope of tangent line, then the integral calculus tell you how to find distance in area of functions. So differential calculus is about tangent problem, tangent and velocity problem. And there is a connection between differential calculus and integral calculus, and they are connected with one another through a theorem is called a fundamental theorem of calculus. So let me cover fundamental theorem of calculus part 1. Fundamental theorem of calculus part 1. It say that if f is continuous on a closed interval from a to b, then the functions you have a function of this form, g of x equal to the integral from a to x of f of t dt for t is between a and b. You have this function, and this function is also continuous on the interval from a to b. And there's a differentiable function on an open interval from a to b. And now when you take the derivative of this function, so you take g prime of x or d dx of this definite integral, what you get is the integrand, so f of t in this case called the integrand, but in terms of x, right? So the function you obtain is going to be this function, exactly this function, but it's in term of x instead of in term of t. So that's the connection. That's the first connection, that you take derivative on an integral in a way, even though it's not mathematically correct to say it, but it's convenient for us to say that is the derivative cancel out with integral, and you get the answer f of x. So a few things here when you have this type of formula. That is the notations here, or the variable that you want to work with right here. They have to be the same, right? So this x and this upper limit of integration have to be the same. So should be same as g of x and g prime of x. Right? So they have to be the same in order for the theorem to work. The lower limit of integrations you have right here. So they have to be always a constant. And again, at the end, your result has to be f of x. The variable here is the same as g of x and g prime of x. And what up here is that this should be always a variable. So the lower limit of integration always a constant, but the upper limit of integration always a variable. You have to follow this setup. Right? so that the fundamental theorem of calculus is going to work. If not, you have to somehow manipulate the integral so that you put it back into this form. That is the derivative of an integral where the lower limit of integration has to be a constant and the upper limit of the integration has to be a variable. And the variable of consideration has to be the same with the variable that you want to take the derivative on. Okay, so let me give you some example here. It's going to be very straightforward calculations to give you an idea that when you apply derivative operator on the integral operator, they cancel out. Okay, let's take a look at the following example. So example 1, you want to find the derivative of the function that is the function of the form g of x equal to 0, the integral from 0 to x of square root of t squared plus 1 dt. All right. So let's take a look at this function. So this function is the definite integral from 0 to x. X is the variable, right? So this setup agree with our requirement here. The lower limit of integration is a constant always. So here is a constant. The upper limit of integration has to be a variable. And the variable is the same as g of x. Okay. Now to find the derivative of this function, you just do, so g prime of x equal to d dx of the integral from 0 to x of square root of t squared plus 1 dt. Okay. Again, the lower limit of integration is a constant, the upper limit of integration is a variable, and this variable is the same with g of x, right? The same with g prime of x, and the same with the variable that you want to take derivative on. Okay. When everything is agreed with the requirement, we're going to just pull down the answer. Just take the integrand, right? So this is the integrand. So let me make that clear. This is the integrand. All right. Just write the integrand. Everything should be the same, except you switch the variable t to the variable x. That is the answer. Okay. As you can see, the integrand here get bring now as the answer, but the variable gets swapped from t to x. And that is the answer. That's it. Hopefully that's straightforward enough for us. Okay, so again, in a way, for the fundamental theorem of calculus, part 1, you apply derivative operator on integral operator. Everything cancel out, and you're left with just the integrand. Now we're going to move on to example 2. We have that g of x equal to the integral from 0 to x of t to the 5th power minus 9 times t cubed dt, and you would like to find g prime of x. Okay. So here's the setup. So g prime of x, what is it going to give you? So you take d dx of the integral from 0 to x of t to the 5th power minus t 9 times t cubed dt. So what do you got here? The lower limit of integration is a constant that we got. The upper limit of integration is a variable. And the variable is the same with g of x, the same with g prime of x, and the same with the derivative that you want to take on, the variable that you want to take the derivative on. Right? So everything agree with one another. Therefore, for the answer, you just bring the integrand right here. That is the answer, because derivative and the integral operators cancel out, you're left with just integrand, but the answer should be in term of x only. So this is x to the 5th power minus 9 times x cubed. Now for example 3, you want to calculate the derivative of d theta of the definite integral from 1 to theta of cotangent of u du. So here's again the setup. The lower limit of integrations is a constant. We got that. The upper limit of integration is the variable, where the variable is the same with, in this case, should be g of theta or g prime of theta, and also the derivative, the variable where you want to take the derivative on. Okay. And everything is agree with one another. And this is the integrand. Therefore, the answer should be just cotangent of theta. So you see, for this one, so far 3 examples, everything's agree with one another when we do the analysis. Now, when we move on to example 4, what you're going to see is that the setup is not going to be the same with what we're looking for. Okay, so example 4. So find the derivative of the functions. The function is of the form g of x equal to the integral from x to 0 times square root of 1 plus cosine of t dt. Okay, so you want to find the derivative on this function. So g prime of x is equal to d dx of the definite integral from x to 0 of square root of 1 plus cosine of t dt. All right. So a couple of things when you notice this setup is that the lower limit of integration is not a constant, and the upper limit of integration is not a variable. So therefore, you have to swap the limits of integrations. All right, so what you have here is d dx, negative of the integral from 0 to x of square root of 1 plus cosine of t dt. So you see the difference here between the original function. So the integral from going from x to 0, now it gets swapped back from 0 to x. When you swap the directions like that, you input the negative into the functions. Right, so negative, that means -1, so that is the constant multiple. You can pull the constant multiple out of the integral or derivative operations. So now the functions becomes, or the derivative becomes negative of d dx of the integral from 0 to x, square root of 1 plus cosine of t dt. Now we do the analysis quickly again. So the lower limit of integration again is a constant, which is good. That's what we need. The upper limit of integration is a variable. And this variable, I agree with g of x, with g prime of x, and with the variable when you want to take derivative on. Now you have the integrand here. And the answer should be just the integrand, but in terms of x. Right? And again, don't forget you have a negative sign in front of the calculation or in front of the results. So you get negative of square root of 1 plus cosine of x. All right, so one more example on this particular theorem. So example 5. Find the derivative of the functions g of x equal to the integral from x to 1 of tangent of t dt. So the derivative of the function is going to be g prime of x equal to d dx of the integral from x to 1 tangent of t dt. Okay. When we do the analysis for this particular setup, to see that the lower limit of integration is not a constant and the upper limit of integration is not a variable. So you want to swap the limits of integrations. When you swap the order of the limit of integrations, you need to put the negative sign. So here you get d dx, negative of integral from 1 to x of tangent of t dt. And again, in this case, the negative sign is the constant multiple, so you can bring that out of the derivative operations. And you should get negative of d dx of the integral from 1 to x, tangent of t dt. So this is the variable, right? So that upper limit of integrations. The lower limit of integration is a constant. And the integrand is here. When you perform the calculations, again, the idea of fundamental theorem of calculus part 1 is that you apply derivative on integral, they cancel out, you're left with just the integrand, but in terms of the variable on the upper limit of integrations. So here you get tangent of x, but don't forget there's a negative sign in front of it, so you put in the negative sign. Then that's it for the fundamental theorem of calculus part 1.